Okay, we'll start in with section 9.5. I'm going to call this part one and bust this up into two separate videos so it doesn't get overly long because there are two kind of separate subjects in this section. This section is entitled the Alternating Series Test, or very cleverly abbreviated AST. It works off of the harmonics. So to remind you, the harmonic series is a simple fraction, 1 over n, sum from 1 to infinity. If you write out the terms, 1, n is 2, plus a half, plus a third, plus a fourth. This is a p series. The p is the power on the n. It's not shown because it's 1. And this diverges because this will add bigger and bigger and bigger forever. Okay, and by the way, this will, the, the harmonic series will occur the rest of the chapter in different spots, and it can occur with all the signs negative. So just to point that out, if I have put a negative in front of the sum, then each term is negative. You can factor out that negative and you get the same harmonic, and it still diverges. So all the signs can be positive or all the signs can be negative. So if all the signs are the same, either all positive or all negative, it is harmonic and it diverges. So someone very smart came along and wondered, what if we alternated the signs? And that would look like this. And what they did was insert a term that looks something like this, that is simply there to literally alternate the signs. I write out the terms. If you start with n is 1, up here 1 plus 1 is 2. That's going to give you an even power, making the first piece positive. But if n is 2, 2 plus 1 is 3. Odd power on negative 1 gives you negative, and you have negative a half. So every odd value of n will give you a positive term. Every even value of n, when you add 1, turns it odd and gives you a negative term. Every other term is therefore subtracted out, giving you a much lower sum. So they were wondering, would this be enough to lower the sum to make it converge? By the way, the sign switching term does not always look like what I just showed you. It can look like minus 1 to the n, a minus 1 to the 2n, a minus 1 to the 2n plus 1. Sometimes it even looks like a sine or a cosine. If you can think back to your trig, if n is 1 here, cosine of pi is negative 1. And if n is 2, cosine of 2 pi is 1. And all this does is switch back and forth between minus 1 and 1. Same thing with sine, although you need a pi over 2 to be up and down on the unit circle. N is 1, sine pi over 2 is 1, n is 2. So L sine pi is 0. You may have to add an n plus 1 in here. I mean, I have this exactly right, but you'll see occasionally they can jigger it around with a sign. These kind of terms are not considered part of the actual term. They are just there to switch signs. So this very smart person figured out a test for when this alternating series will converge. Page 623, the AST, the alternating series test. It has two conditions. It will converge if these two conditions are true or work or are satisfied. First of all, the limit of the terms must equal 0. And again, that term does not include the sign switching term. And then does an plus 1 less than or equal to an? In plain English, the an is what is given in the sum. That's called the nth term or the current term. And an plus 1 gives you the next term. That's what I'm saying down here. You plug n plus 1 in for the n, and you get what the next term looks like. So in effect, the next term, this an plus 1, must be less than the current term. And this means that the terms are getting smaller as you go out to infinity. Those two conditions are met, and alternating series will converge. All right, so apply this AST to an alternating harmonic series. So once again, they insert a sign switching term and you have 1 over n. Now, when I say ignore this, I mean for the purposes of the AST, first condition, the AN is simply whatever they give here, not the sign switching part. You can see very quickly that the limit as n goes to infinity of 1 over n is 1 over infinity and gives you 0. So that condition is satisfied. Now to check the second condition, you sub in n plus 1 for that n, giving you 1 over n plus 1. Is that less than or equal to 1 over n? Well, if you notice, n plus 1 is bigger than n on the bottom here. So when you put them on the bottom of a fraction, the overall fraction will be smaller. And that will be true for all n. So the second condition, yes, is satisfied. Therefore, this leads to a very technical conclusion. Since this alternate harmonic series satisfies both conditions of the AST, it converges. So to summarize, a straight harmonic looking like this with all positive or all negative signs diverges because the sum will either get bigger and bigger all positive or bigger and bigger all negative. But the alternating harmonic series we just showed satisfies both conditions of the alternating series test, and it converges because it satisfies the AST. This is a very important result for the rest of the chapter. A harmonic series diverges, but the alternating harmonic series converges. That's going to come up the rest of the chapter. Try a homework example. Page 629, number 9. They have kind of jumbled together the sign switching part with n plus 1. I should have written another step to separate it out to make it really more obvious. You could write a 1 over n plus 1 over here to make it more separate. You'll see a lot of times the sign switching is jumbled in with the term. But we're going to check this by the AST. I've written out the terms. It clearly alternates signs if you plug in n, because the sign on the -1 alternates between odd and even. So when I run the AST and I'm checking the limit as n goes to infinity of the term is only 1 over n plus 1. Plugging in infinity, 1 over infinity, sure enough, gives you 0. When I check the second condition, an plus 1 less than or equal to the current term an, I only plug in n plus 1 where the n is. So that's 1 over n plus 1, therefore the n plus 1. Is that less than or equal to the nth term, which is 1 over n plus 1? It was given to be n plus 1. I know that's a little confusing, but the nth term given this way has just straight n plus 1. And the n plus 1 term will actually have 1 over n plus 2 because I've plugged in n plus 1 for the n. And sure enough, by the same argument, n plus 2 is bigger than n plus 1. So on the bottom of a fraction makes the fractions smaller, and the second condition works. So we conclude that sum of -1 to the n plus 1 over n plus 1 converges by the AST. We're going to end that with part 1, and we're going to pick up with part 2.